Swayam Prabha. Digital India. Educated India.
Welcome to the course on micromachining under DTH. Today I am going to talk about ultrasonic micromachining. Organization of the talk: Introduction to ultrasonic micromachining, theoretical analysis of ultrasonic machining and ultrasonic micromachining, parametric analysis and process characteristics, some applications of ultrasonic micromachining, and then conclusions. Some references where from I have taken this particular part of my talk is R.S. Jardon, then again chapter 9 of R.S. Jardon written on ultrasonic micromachining in the book on Introduction to Micromachining, published by Narosa Publishers. And this is the lecture delivered by Professor R.S. Jardon on ultrasonic micromachining in the short-term course at IIT Kanpur. Then you have some books on advanced machining processes, Introduction to Micromachining and Micromanufacturing. Introduction to ultrasonic micromachining, Part 1. Ultrasonic micromachining. What is ultrasonic? This is vibratory waves having frequency greater than the upper frequency limit, that is greater than or equal to 16 kHz of the human ear. There are two types of waves, ultrasonic waves. One is known as longitudinal wave. They are used in ultrasonics. They easily propagate in solids, liquids and gases. And second are the shear waves. Longitudinal magnetostriction: if a ferromagnetic material is placed in continuously changing magnetic field, then it results in a change in length of transducer. That is magnetostriction type transducer. That transducer is known as magnetostriction type transducer. The normal material used for this purpose are nickel, permalloy, 45% nickel, 55% iron. This is permalloy, ALLO by, not R. Permidior, 49% cobalt, 49% iron, 2% vanadium. It is made of laminated sheets. It reduces eddy current losses. Functions of ultrasonic transducers, we will discuss it. And it converts any form of energy into ultrasonic waves. Electrical energy is converted into mechanical energy, that is in terms of high frequency vibration in case of ultrasonic micromachining. Features of macro and micro ultrasonic machining I have already mentioned in other lectures. If it is greater than 1 millimeter, it comes under the category of macro. If less than 1 millimeter, it comes under the category of micro. Now, in case of ultrasonic machining, vibration frequency is usually greater than 20 kHz, while it is also 20. Vibrated part: tool and workpiece. Tool in case of macro ultrasonic machining. Amplitude of vibration 0.5 to 5 micrometer. In case of macro, it can be 8 to 30 micrometer. Average particle size in case of micromachining 0.5 to 5 micron size, and here it can be tens of micron size of the abrasive particle size, 50 to 300. Static load in terms of gram force, while here it is in gram force, and tool feature size in millimeter is within 0.5, because depending upon the size of the tool, you are going to get the size of the feature in case of micromachining as well as macromachining. Ultrasonic micromachining, a valuable process for the precision machining of hard and difficult to machine materials, including electrically conductive as well as electrically non-conductive material. This is very special characteristic of this particular process. There is no constraint on the electrical conductivity of the workpiece material. It is able to micromachine electrically non-conductive, brittle and hard materials such as glass, silicon, quartz crystal, sapphire, nitride, ferrite and fiber optics. Ultrasonic machining can be used to drill holes smaller than 10 micron size. Ultrasonic micromachining has been developed by introducing fabrication of micro tools on the machine itself, and this is very important. Wherever you are going to perform micromachining process, then and there itself the micro tool are fabricated, then the same tool in the same machine tool is used for micromachining purposes. So it says, and then applying ultrasonic vibration and rotation to the tool or to the workpiece during the drilling process. This is another point to note, that rotation can be given either to the tool or to the workpiece in case of micromachining, especially in case of micro drilling process. Ultrasonic micromachining is a combined micromachining method capable of machining various 3D microparts made of almost all kinds of material. That material restriction we have already seen. There is hardly any material restriction as long as thermal and electrical conductivity are concerned. Wire EDG or EDM process can be used for preparing coaxial micro tool first, and then this micro tool is used directly in ultrasonic micromachining. Normally we avoid to transfer this micro tool to some other machine tool because dimensional problems and coaxiality comes into picture. Ultrasonic transducer can be used in two ways. The first system oscillates the tool, and the second system does not oscillate the tool but it oscillates the workpiece. I will show you some pictures or photographs related to this to make it more clear. Elements of ultrasonic micromachining system. You can see sine wave generator is there, transducer is there, tool holder is there. Then on the other side you have workpiece, tool and abrasive particles. We will discuss them in detail. Working of ultrasonic machining and ultrasonic micromachining system. Please note it carefully that working principle of both the processes, macromachining as well as micromachining, remains the same, except the process parameters and abrasive particles and fluid that you are going to use, they will change. AC power supply, ultrasonic wave generator, then you have ultrasonic transducer, tool connector is there to the transducer, and then you have the tool, and tool it is vibrating at ultrasonic frequency, and beneath the tool and above the workpiece surface slurry is there, and that slurry is having the abrasive particles, thousands and thousands of abrasive particles. So those abrasive particles get vibrated because of the vibration on the tool. We will see the picture also for this, and this vibration of abrasive particles hits the workpiece surface, and because of the kinetic energy and or hammering action of these abrasive particles erodes the material from the workpiece. Thousands of craters on the workpiece are created because thousands of abrasive particles are hitting the workpiece surface at high kinetic energy, which is creating the crater on the workpiece surface, and finally you get finished component. You can see here very simple picture. This is the concentrator, you have the vibrator over here, you have the abrasive slurry being supplied over here, here is the workpiece, and this is the tool, and this is vibrating at ultrasonic frequency, so that vibration is transferred to the abrasive particles. By that vibration it hits the workpiece surface and removes the material. You can see here better picture. This is the tool which is vibrating at ultrasonic frequency. These are the abrasive particles in the slurry, and when this tool is vibrating, that vibration is transferred to the abrasive particles and they hit this workpiece surface with certain kinetic energy, which is sufficient to remove the material from the workpiece and create a crater over there. Tool size is in microns in case of micromachining, definitely, otherwise you are not going to get micro features over there. These are the transducer binding. Now this is the tool schematic diagram for which we have already seen. This is the slurry, abrasive particles, tools are there, this is vibrating at ultrasonic frequency. So tool is approximately inverse replica of the desired hole or cavity in the workpiece. Whatever is the shape and size of the cavity that you want to create in the workpiece, the tool has to have inverse shape of that particular cavity, and accordingly the dimensions are maintained. Tool is positioned near the surface of the workpiece. This is the surface of the workpiece, this is the tool. The working gap is flooded with slurry, that is over here, and comprising water and abrasive particles. Impact from the tool propels the abrasive particles across the working gap. Abrasive particle hits the workpiece with a force. This force is very small, hence it gives very low overall cutting efficiency. So you can see here, this is the micro tool, and you can see different parts over here. Here if you see on the left side, one is the wire EDG system which is used for preparing the micro tool over here. Then you have the ultrasonic transducer is 2, and 3 is the cone over here, and 4 is the horn, that is known as horn also, and 5 is the micro tool, and 6 is the ultrasonic generator, 7 is the motor controller over here. You have the 7 is the motor controller and you have 4 different motors for controlling X, Y, Z axis and C axis. And then you have the machining stage over there, and here is the 9 is the workpiece, this is the workpiece, and slurry system is there 10, it is being supplied through this nozzle, and acoustic emission system is there over here, and personal computer is here. So with the help of the personal computer, you are going to control the system. This is another arrangement of the same type of the machine. You can see here vibration is given to the workpiece, that 4 is given the vibration, here vibration is given to the tool. This is the basic difference between these two configurations. As you can see here, tool vibration type 1 system and workpiece vibration type 2 system. So you have to keep in mind, because I will be discussing model 1 and model 2 in the following lecture, and this has been taken from the chapter of the book. Methods of applying the static load during ultrasonic machining and ultrasonic micromachining. These are the 4 different methods normally used. One of them used to apply the static load during ultrasonic micromachining. This is a counterweight, and this is rest of the part. Here we put the tool over here, so this static load is being applied through the counterweight. Here you are applying pivoted counterweight. This is pivoting here, weight is over here, so you are applying the load on this particular tool that is to be mounted here. Then you have the spring loaded system, and finally you have the pneumatic or hydraulic system through which you are applying the load or the force on the tool that is to be mounted over here. Working principle of ultrasonic machining and micromachining: electrical energy of high frequency is converted into mechanical vibration through a transducer. Transducer is converting this energy into the mechanical vibrations. Mechanical vibrations are transmitted to the abrasive particles. We have seen in earlier figures how it is transferred through the slurry via an energy focusing device, that is horn or tool assembly or concentrator. I have shown you in the earlier figure also the concentrator. Transducers are of basically two types depending upon what kind of power you need from the transducer. You have piezoelectric transducer and magnetostrictive transducer. You can see here piezoelectric transducers, they give higher energy efficiency and no cooling is required, no heat damage liability and low power capacity. This is the main reason that there is no damage and no cooling required, because power obtained from piezoelectric transducer is comparatively low. But in case of magnetostrictive type of transducer, two things are there: you have low efficiency and high power capacity. It can give you as high as 2400 watts or even more than that. Anyway, we can see quickly here ultrasonic machining for the machining of hard and brittle materials such as glass, etc. Because of the difficulties faced in fabricating miniature size tools and their mounting on ultrasonic machining setup, USM could not achieve formation of precision holes less than 100 micrometer in diameter. We are talking about USM, and USM tools are directly attached to the horn by soldering, brazing or screwing, making it difficult to maintain the accuracy of the tool concentricity. This tool concentricity is very important, because if the tool is not concentric to the axis of the horn, then you will not get the correct size of the machine feature. In case of ultrasonic micromachining has been developed by introducing fabrication of micro tools on the machine itself. This is what I have emphasized earlier also, that on whichever machine, whether EDG machine or EDM machine, you are fabricating the micro tool, on the same machine too, you are doing ultrasonic micromachining, so that concentricity, axis coincidence takes place. It applies ultrasonic vibration and rotation to the tool or to the workpiece during the drilling process. I have already shown to you, it may be either tool or workpiece, capable of machining 3D microparts made of almost all kind of materials. Removal of material in 3 modes as proposed by L. Chinda et al., because different modes have been proposed by different researchers. Here this gentleman has proposed 3 modes, that is the mode A, mode B, mode C. In mode A, it is the erosion that is taking place. In mode B, colliding or sliding, and in mode C, small scale removal action, that is shown over here. You can see here small scale removal, so exciting abrasive particles are there, so total force acting is comparatively low, and this is the workpiece from where you are removing the material. Schematic illustration of the modes of material removal in non-contact ultrasonic machining. Some authors have proposed 4 modes: abrasion, microchipping, cavitation and chemical action. Here we are not considering the chemical action. Impact force due to cavitation collapse, it can be, size can be 0.5 to 5 micron. Mode A, the size of the cavity created in mode A, as we have seen in the earlier slide, can be 0.5 to 5 micron, depth can be 0.05 to 1 micron, and shape can be round Mars. In colliding or sliding of abrasive, mode B, the size can be 0.3 to 1.5 micron, depth can be 0.01 to 0.3 micron, as you can see, it is smaller than A. Irregular shape marks, wedge shaped pits or scratches, and small scale removal action by exciting abrasive mode C. Yes, this is smaller than this even. 40 to 60 nanometer is the size, 3 to 6 nanometer is the depth, and non-nano scale marks are there. So you cannot define them accurately which shape the feature or the cavity is created. Variants of microsystem. Now you can have microchipping, abrasion, cavitation, chemical action as the 4 variants of removal of the material. Now you can see here slurry nozzle, this is the micro tool, these are the abrasive particles, and this is the workpiece. So debris are there, the material removed from the workpiece known as debris, and this is the uncut chip. Acoustic head. The acoustic head, which is one of the most important components of ultrasonic micromachine tool of first type, consists of 2 parts, transducer and horn. Horn, also known as acoustic coupler, velocity mechanical transformer, tool holder, concentrator, shank, stub or sonotrope. The amplitude of the vibratory motion of the transducer is small and is usually inadequate for material removal purposes. The horn amplifies and focuses this vibration of the transducer necessary to drive the tool to do its work. That means this size has to be increased. It is very small for machining purposes. So this you have the horn which amplifies the vibration so that this size increases. The increase in amplitude of vibration at the tool end is obtained by reducing the cross section of the tool end. As you must have seen in the horn, it is tapered one, kind of tapered one. Optimum tuning is specific for each horn material. Horn material should possess the characteristics like high mechanical Q. Q is a measurement of the sharpness of the peak value of the energy. Good acoustic transmission coefficient. High fatigue resistance at high working amplitude. Good breathability. High corrosion resistance, etc. Because this high fatigue resistance at high working amplitude is very important, otherwise horn itself may fail, because amplitude of vibration is large as well as frequency of vibration is also very high, 20 kHz or more than that. The most commonly used horn materials are monil, titanium, AISI 304, stainless steel, aluminium and aluminium bronze. High frequency oscillating generator. The power supply used for ultrasonic micromachining is more accurately characterized as a high frequency oscillating current generator. It offers the user with a control over both the frequency and power of the generated signal. Sine wave generator, it converts 60 Hz to greater than or equal to 16 kHz. Tool holder, there are 2 types of tool holder, non-amplifying tool holder and amplifying tool holder. This amplifying tool holder, it can amplify 10 times higher amplitude than non-amplifying tool holder amplitude. It transfers energy, tool holder, and amplitude of vibration 1 micrometer to 0.1 micrometer. Material for tool holder. Commonly used material for tool holder is monil, titanium, stainless steel. Whatever material you are selecting, it should have good acoustic properties. Also, it should have high resistance to fatigue cracking. Because of these vibrations, It should have good resistance to fatigue cracking, otherwise this itself may fail. And it should avoid welding between tool holder and transducer because they are having high frequency vibrations. Then you have the tool material, mild steel, stainless steel, brass, ductile, high wear resistance. Now I have given you different types of the tool material and so on. Don't get confused. Depending upon your requirement, frequency of vibration and amplitude of vibration, you have to select a right kind of tool material. Surface conditions, good surface finish. There should be no scratches, no machining marks on the tool surface, otherwise it will affect the accuracy of the machine surface. Tool design considerations for overcut should be given because whenever you are doing ultrasonic machining or ultrasonic micromachining, and whatever is the size of the tool, whatever cavity you are getting, it will be slightly larger than the size of the tool, and that is what is known as overcut. So overcut should be taken into consideration while designing the tool for ultrasonic machining as well as ultrasonic micromachining. Minimize fatigue problem by silver brazing of tool and tool holder. Transducer, ultrasonic micromachining transducer converts high frequency electrical impulses received from the generator into high frequency mechanical vibrations. Two types of transducers for ultrasonic micromachining are based on two different principles of operation. One is piezoelectric, another is magnetostrictive type transducer. Piezoelectric crystal, quartz transducer, it can give up to 900 watts. I have already told you. Efficiency is good, 95% efficiency. It is used for non-destructive testing, cleaning, machining, etc. It eliminates the need for water cooling because total power is quite small comparatively, so it does not require water cooling of the transducer. Not liable to get damaged due to heat because heat generated is very low. It appears to be more easily adaptable for rotary operations. Magnetostrictive type transducer, that is second type, it can give you up to 2.4 kilowatt as a power or even more than that, and the efficiency is 20 to 30% only, and by in piezoelectric efficiency is around 95%. So you can compare the two. Cooling is essential because lot of heat losses are there, so temperature rises, so you definitely need the cooling. It needs water cooling to remove waste heat. High electrical losses results in low energy efficiencies, comparatively low vibration intensities. Power capability up to 2400 watts as mentioned here. Maximum amplitude of vibration around 25 micron. Length change achievable by both types of transducer is approximately 25 micron. Constructed from a laminated stack of nickel alloy sheets. The amplitude of vibrations is amplified through horn in first type of machine tool, whereas second type of machine tool does not require amplification, because in second type of machine tool, if you remember, workpiece is vibrating rather than the tool. They directly vibrate workpiece instead of the tool. CNC control is very important so that different parameters of the process are automatically controlled by the machine itself. In ultrasonic micromachining, tools are very small. Coordinate information from the tool making stage to the actual machining stage is required. That is very, very important. Otherwise, you are going to get inaccurate cavities or the features. Computer numerically controlled 4 axes are there: X, Y, Z and C axis. X, Y, Z axis are driven by stepping motors, and the lead screws with a step feed of 0.05 micrometer. That means this is the accuracy of movement 50% 0.05 micrometer or 50 nanometer. The C-axis is driven by a DC servo motor. You can see coordinated system used in ultrasonic micromachining. This is the C-axis, X-axis, Y-axis and Z-axis over there. C-axis for rotation, Z-axis is in this direction. C and Z both are there, and X and Y. Here Z is over here, slightly different. They both are not matching. This X-axis of the tool is not matching with the Z-axis. Abrasive slurry, Al2O3, silicon carbide, boron carbide. Abrasive hardness should always be greater than workpiece hardness. This is the point to be noted, otherwise it will not be able to machine any workpiece material. Selection criteria, one should consider hardness, size, life and cost of the abrasive particles, workpiece material hardness plus desired material removal rate and surface finish. These are the criteria which will decide which abrasive particles and what size of abrasive particles should be used. And low concentration, deep hole drilling, complex cavities, etc. If you are doing this, then you can have the low concentration of the abrasive particles. And process performance, that is normally measured in terms of material removal rate or surface finish. It depends upon grain size or abrasive particle mesh size, which is normally given in terms of 240 to 800. These are not micrometer. This is the grain size normally given in these numbers. Supply medium, slurry medium, water, benzene, glycerol, etc. can be used. Now this will be decided based on what is the complexity of the feature that you are creating and what is the depth of the feature. If it is high depth, then you should not use high viscosity slurry medium like glycerol. Best results are obtained with low viscosity, but it may corrode the workpiece surface. Water is used for best results. It has low viscosity, but there is danger that it may corrode the workpiece surface. Abrasive particles, actual cutting tools in ultrasonic micromachining, they are real cutting tools. Slurry consists of small abrasive particles mixed with water or sometimes with oil. Abrasives have concentration of 30 to 60% by weight. Criteria for selection we have already seen: hardness, usable life, grit size and cost. The abrasive particles used for an application should be harder than the material being machined. I have already mentioned that workpiece material should be much softer than the abrasive particle hardness. Abrasive size varies between 200 to 2000 grit size. This is COARSE. Coarse grades are good for roughing and finer grades are used for finishing. Abrasive slurry supplied across the tool face by jet flow, suction or a combination of both, depends upon your requirements. Abrasive slurry, it acts as a coolant for the hod, tool and workpiece, all the three, because its temperature is room temperature. It supplies fresh abrasive to the cutting zone and removes debris from the cutting area. Whatever material is removed in the form of chips, that is also known as debris. So it has to be removed from the cutting area, otherwise efficiency of machining will go down. Abrasives transport medium characteristics are as follows: low viscosity with a density approaching that of the abrasive, good wetting properties, preferably high thermal conductivity and specific heat for efficient cooling. Because temperature has to be maintained, otherwise its viscosity is going to change, and if viscosity is going to change, its performance may also change. Water meets most of these requirements as mentioned over here. Wear of abrasive particles is also an important factor because the material removal rate is dependent on the particle size. If wear of particle is more, then its shape and size both are going to change during the process, which is going to affect accuracy, material removal rate, and maybe to some extent the shape of the machine cavity. Workpiece, no limitation to the range of materials that can be machined, except that they should not dissolve in the slurry media or react with it. Kramer and Benkirain has classified workpiece material into three categories. First category of the workpiece material, high fragile and porous materials like glass, germanium, ceramics, quartz and silicon, etc., that are machined very easily with high material removal rates and low tool wear rates. Second category, less fragile or porous materials like ceramics, oxides or carbides and precious stones that are more difficult to machine. And third category, either very hard or very ductile materials such as silicon, nitride or diamond that are well resistant to the process, but poor material removal rates and high tool wear rate because they themselves are very hard. So you have poor MRR and high TWR, tool wear rate. Ultrasonic micromachining must be used for machining of first category material, that is first category materials. Second category materials should be machined when it competes well with other processes. In second category, if you don't have other processes to machine efficiently and economically, then only you should go for ultrasonic micromachining, otherwise use that particular process. And the third category of material, that is this one, should be machined only when no other process is effective, because there are many processes which can be used for micromachining. Say abrasive jet micromachining is there, or for electrically conducting materials like electrochemical micromachining, electric discharge micromachining and so on. So this system I have already shown to you earlier. Here workpiece is vibrating as shown over here. 4 is the ultrasonic transducer. This is vibrating the workpiece surface, that is the workpiece is mounted over here, 6 number, and this is vibrator. Harder materials are cut by brittle fracture, whereas softer ductile materials are cut by shearing action, that we already know. Machinability depends on workpiece mechanical properties and fracture behavior of the workpiece material. Micro tools, micropin machined by wire electric discharge grinding process. You can see here original part was having this much diameter and final part is having 5 micron diameter. So this is known as micropin machined by wire EDG process. On the same machine you are going to perform ultrasonic micromachining. Product dimensions depend on the tool dimensions defined by the workpiece requirement. Fabrication of micro tool is a real challenge in ultrasonic micromachining. That's what I have told you already, that either wire EDG or EDM process is used for it, and sometimes EDG process is also used. Vibrations at tool end result in problems of difficult tool holding and machining inaccuracies. On the machine, tool preparation, electrode soldered to the machine head prior to its preparation. That's what I have told you, same machine, you solder it, then machined by wire EDG to the desired dimensions and the subsequent machining was done or is done on the same machine tool. This is same machine tool is very important for 20 micron or more. Very difficult to achieve deep micro hole due to tool vibration. New methods to overcome vibrations were applied to the workpiece. We have already seen it. To minimize the tool wear, tools should be constructed from a relatively ductile materials such as stainless steel, brass and mild steel. This is very important to note. The harder the tool material, the faster its wear will take place. Tool material used should have high wear resistance, good elastic and fatigue strength properties, and have optimum values of toughness and hardness for the application. Properties of tool material affect the penetration of the abrasive grains into the workpiece and the tool, and hence influence the machining process. Please note here it is written penetration into the workpiece as well in the tool, because the abrasive particles are in contact with the workpiece as well as the tool. As we will see later on, it may penetrate inside the workpiece or inside the tool. The geometry and cross-sectional areas of the tool have considerable influence on material removal rate, that is MRR. A lower limit on the thickness of the tool has been suggested to be not less than 5 times the abrasive grit size. Whatever is the size of the abrasive particle in terms of micrometer, the tool has to be 5 times thicker than that, so that sufficient abrasive particles are hit by the tool to penetrate inside the workpiece. Tool wear tends to increase when harder and coarse abrasives are used. Generally, tool wear with tungsten carbide and stainless steel tools is observed to be lower when compared with mild steel tools. So it depends upon the tool properties. Variants of micro ultrasonic machining. Micro ultrasonic machine tools. You can have stationary micro ultrasonic machining with tool vibration or with workpiece vibration. Whatever we have discussed, it is summed up in this particular diagram. Micro rotary ultrasonic machining with tool rotation or with workpiece rotation. Hybrid ultrasonic machining, where you have ultrasonic machining plus EDM. This is used for preparing the micro tools. Ultrasonic machining plus AFM, abrasive flow finishing or abrasive flow machining. This is used for finishing the tool. And then you have the ultrasonic assisted turning or drilling. Tool head, you can have mode 1, where solid cylindrical tool is used or hollow tool is used. In the second case, pattern tool is used. Depending upon your requirement for the cavity or the feature, you can pattern the tool and then use it as a tool, so that inverse replica of the tool shape will be produced on the workpiece. Ultrasonic machining systems. Following 2 types of the ultrasonic machining micro machining system have been developed. We have already seen first type, ultrasonic micro machining system, in which ultrasonic vibrations are applied to the tool. In the second type, it is applied to the workpiece surface. Theoretical analysis of ultrasonic machining and ultrasonic micro machining. Here I will like to emphasize, whatever is the theory applied for ultrasonic machining, that is macro machining, same theory is applicable as of now for ultrasonic micro machining. Mechanism of ultrasonic machining and ultrasonic micro machining. It was proposed basic component. It was proposed by M.C. Shaw, late M.C. Shaw, proposed basic components to the cutting action. Direct hammering of abrasive into the workpiece by the tool that is the major factor, means abrasive particles are directly hit by the tool. That means tool is touching the abrasive particles, the impact of the abrasive on the workpiece. Second, cavitation induced erosion. We are not discussing this cavitation induced erosion in this particular lecture. Third, chemical erosion caused by the slurry. This also we are not discussing here. Experimental setup for ultrasonic machining and ultrasonic micromachining. You can see here, this is the real life machine tool for ultrasonic machining. Dial indicator is there, pneumatic system is there, then you have the tool over here, workpiece is there, this one, then you have the electrical connections, and this is the converter, then you have the coupler, and then the horn, and then slurry circulating hose with nozzle end. So this is the nozzle end. Tabletop stand is there. Our machine is mounted on this particular stand. Analysis of material removal rate. This was proposed by MC Shaw model. Assumptions were made. Abrasive grains or abrasive particles are spherical, having diameter as small d, that is equal to 2r capital. Volume of the particle chipped off from the workpiece surface is approximately proportional to d, that is the diameter d here, and is equal to half the volume of a sphere of diameter 2r. Note 2r is not equal to d. A sphere that is created is different than the abrasive particle diameter. Other modes of material removal are cavitation, chemical action. They are neglected or they are not being considered here. Material removal by throwing mechanism and hammering actions are considered in this particular case. I will show you. While you are hitting an abrasive particle, it will go and hit the workpiece surface, and because of kinetic energy it will remove the material. In the hammering model, you are just hitting the abrasive particle between the tool surface and the workpiece surface, and it is touching both of them at the same time. So that is the hammering model. So both models are different. Radius of the spherical crater created formed due to fracture is r. You can see here fractured volume. H is the depth of penetration, is the grit or abrasive particle, tool and workpiece surface, and this is vibrating at ultrasonic frequency. You can see it more clearly over here. This is the sphere, this is the radius r equal to d by t, 2, r is the radius equal to half of the diameter, and h is the depth of penetration. So r minus h becomes this height of the triangle, and h is depth of penetration, and this is the small r. So this is the radius of the sphere created in the workpiece. So this is the size of the sphere created on the workpiece surface. So please note it carefully, the difference between the small r and the capital R. Development of fracture in the workpiece due to hitting by an abrasive particle. This is the abrasive particle, all of this. Assumptions continued. Radius r in terms of grit radius r and depth of penetration h, this is small h, not capital H, can be expressed as r square is equal to r square minus r minus h whole square. In the previous figure I have already shown to you. So it becomes r square minus r square plus 2rh minus h square. So approximately r square, small r square becomes approximately 2rh, because this r and this r cancel, and since h is already very small, so h square can be neglected. Now volume of material removed per grit per cycle, Vg, is 1 by 2 4 by 3 multiplied by 4 by 3 pi r cube, and if you simplify this becomes 2 by 3 pi 2RH whole raised to power 3 by 2, because R square is approximately equal to 2RH. That is what we have derived in the earlier equation. And this becomes K1 HD, because 2R is equal to small d, HD raised to power 3 by 2, and K1 is the constant which accounts both these terms. So it becomes K1 HD raised to power 3 by 2 millimeter cube per grit per cycle. So K1 is a constant, H and D both are in millimeter. According to the units taken for H and D, the value of the K1 will change, where K1 is constant and H is depth of penetration, and let N, this is K1, this K1, not K, N be the number of impacts per cycle, because in each cycle N particles are impacting the workpiece surface, because there are many abrasive particles under the tool. So when our tool is vibrating downward, certain number of abrasive particles will be hitting the workpiece surface. Inverse function of cross-sectional area of the grit. This N is the inverse function of the cross-sectional area of the grit, as we will see here. This is the small diameter d, this is the diameter d of the abrasive particle, this is the diameter d dash of the abrasive particle. So depending upon the size of the grit, how many abrasive particles can be placed in this particular area will be decided. So that will be N number of abrasive particles or impacts, K2 divided by d square. This is d square. Is every grit active? Now say suppose n grits are there which are under the tool. The question is, which is raised over here, is every grit active? That means, is every grit hitting the workpiece? That hits the workpiece and removes the material. Let K2 be the probability that a grit under the tool is active. So MRR per cycle, it becomes K Vg into number of impacts. Now number of impacts that we are calculating. So you can see here K, K1, K2, HD raised to power 3 by 2 divided by d square. So if you simplify it, you get K, K1, K2 under the root HQ divided by d. So this is what you get, material removal rate per cycle. So MRRV, volumetric material removal rate, will be equal to K, K1, K2, HQ over d under the root multiplied by F. F is the frequency of vibration. So whatever is the frequency of vibration per second, so it becomes cubic millimeter per second. So the question is how to know depth of penetration S, because here K, K1, K2 can be evolved from the experimental data. D is known to us well in advance, F is known to us, H is unknown. So depth of penetration is unknown. Now two models, as I mentioned in the beginning, have been proposed by Shaw, throwing model and hammering model. Now please understand it carefully. When you are hitting the workpiece, when tool is hitting the abrasive particle, it will attain certain kinetic energy, come and hit the workpiece surface, and that is known as throwing model. Here it is throwing the abrasive particles, and with certain kinetic energy it is hitting the workpiece, and this gives you the idea of tool vibration, and A by 2 is the amplitude of vibration and T is the time over here. Throwing model, a grain thrown onto the workpiece by the tool, that is here. Working gap is greater than grit size. Now you can see here, this is the working gap from here to here, and this is larger than the size of the grit over here. Tool displacement or vibration Y from the mean position at t is equal to 0 at time t. I will show you what is this mean positions and other in the following slide. Here, so it becomes Y is equal to A by 2 sine 2 pi 2 ft. Now velocity of tool v, that becomes pi af, because dy t will give you the velocity of the tool, pi af cos pi 2 ft, because this 2 when comes out, this will be cancelled by this. So maximum velocity will be pi af, that is pi af shown over here, assuming that the grit also leaves the tool at this maximum velocity, because here you can see this grit is leaving the tool when it is hitting the abrasive particle, and we are assuming that the velocity of the grit is the same as the velocity of the tool at that point of time. So kinetic energy of this abrasive particle hitting the workpiece surface becomes half mv square, we already know. So this is a half, this is the mass of the abrasive particle, 1 by 2 pi upon 6 d cube, rho a is the density, and this is the maximum velocity we have already calculated, that is here v maximum. So pi square a square f square, so this becomes half mv square h, the kinetic energy of the abrasive particle. If it is good enough, then it will be able to remove the workpiece material and form a tiny crater. If the kinetic energy is not good enough, then it will just not be able to remove the material from the workpiece. Kinetic energy absorbed by the workpiece will result in penetration H. Then the average work done will be equal to how much? Half F is the force, H is the movement, that is the depth of penetration. So the work done will be half FH. So F is the force here, H is the depth. Assumption or assuming that the force variation during penetration is triangular in shape, because initially it will be maximum, at the end it will be 0. So average contact stress sigma on the work surface will be brittle fracture or the hardness of the workpiece, because when material is removed, then this should be equal to, this stress should be equal to or greater than the strength of the workpiece, then only it will be able to remove the material from the workpiece. So sigma is equal to F divided by pi hd, this forms the, d is the depth of penetration, sorry, d is the diameter, h is the depth of penetration, so this will form the area and this is the force, so you will get the stress, pi r square to pi 2 rs, that is pi hd, we have already discussed it, and F is equal to pi hd into h, this force becomes equal to h is the hardness. We are assuming here that stress created on the workpiece is equal to the hardness of the workpiece material. It is known that kinetic energy of the particle is equal to the work done, and we have already calculated the kinetic energy of the particle. So kinetic energy of the particle, half mv square, half pi upon 6 d cube rho a, pi square a square f square is equal to half mhh ds. So this we have calculated, this gives you the half mv square, that is equal to the force. H, then you can calculate h, that is the depth of penetration in throwing model, pi a f d under the root rho a over 6h. H is the hardness, rho is the density of the workpiece material, the depth, we know frequency a and pi. This value of h can be substituted in the equation derived for evaluating MRRV by the throwing model. In the same way, h can be derived if the material removal takes place due to hammering action as follows. We have discussed the throwing model, now we come for the hammering model. This model we will discuss in the next class. Thank you very much.